Alright class, so we are going to then touch on the next part of the binary tree. We're going to talk about a specific form of binary tree that we call binary search tree. Now it has a special property, and this property allows it for us to conduct efficient searches on the tree. Now it's just like earlier on when we talk about array, so we can do linear search on an array, right? A linear search on an array essentially is a way to do brute force. When you're looking for something, you look at every possible place in an array. Now, when we sort the array into a sorted array, then allows us to do binary search that improves the complexity of the method. And the reason why we can improve the efficiency is because we can then cut down the search space. So we can essentially do the same thing on the tree as well. Suppose that we want to search for a node on the tree and we do pre-order, traversal, or post-order, or in-order. These are just different ways of iterating over the tree. We still get complexity of O(n). But if we try to arrange the nodes in the tree in such a way that we can organize them to do binary search on them, then we can essentially do something as similar as the binary search. Now, what is this organization? This organization is going to ensure that for any node, we are going to make sure that any value that is larger is going to go to the right, and any value that is smaller is going to go to the left, and this is going to be defined recursively. So that means it is true for every node recursively. Now this is an example, right? So if you look at 29, anything to the left of 29 is smaller, anything to the right is larger. And then if you look at 14, anything to the left is smaller, anything to its right are larger. If you look at 24, nothing on the left, anything to the right is larger. So this is true for every single node, and this is what we call a binary search tree. Now, why is it a binary search tree? Because we can do binary search on this tree. So for binary search, usually we will compute the midpoint, and then we compare to the midpoint to see whether we should go to the left or to the right. Now, for binary search tree, the midpoint practically has been pre-computed. They are embedded within the structure of the tree itself. So for example, what is the first midpoint? The first midpoint will be the root. So if you're looking for a particular number, you start from the root. So for example, if you're looking for 27, so you start from the root, 27 is not at the root, so then you need to decide whether to go to the left or to go to the right. And in this case, going to the left, we go to the left because 27 is smaller than 29, right? So then you go to the next midpoint, which is 14. So 27 is larger than 14, so we go to the right. 27 is larger than 24, we go to the right. And there is 27. So now, at every single time, we can cut down roughly half of the tree by deciding to go to the left or to go to the right. Now, there are other examples of binary search tree. As long as the nodes can be sorted in a particular way, you can define a binary search tree on those objects. In this case, they are names and they are arranged alphabetically. Now, the three key operations that we do on a binary search tree is to search, to insert, and to remove. Now, let's start with the first one. So starting with the search, right? So search essentially is what we have tried earlier. We just start at the root, see whether the root has the value. If it doesn't have the value, you decide to go to the left or to the right, depending on whether it's smaller or larger. Now, this is the method for searching. So you start at the root and you compare the value at the root. If it is the same, then you return it. Otherwise, you either go to the left if the key is smaller, or you go to the right if the key is larger than the root. Now, coincidentally, this is also pre-ordered, right? So you process the parent first, which is to check the value of the root before you go to the left or to the right. So that's why we said earlier, whenever you process it on a tree, you use one of traversal orders as the backbone of the algorithm. Now, this is to search. Now, let's say now we want to insert, right? So we want to insert, and the key thing about inserting is that we need to put the new node somewhere that will still preserve the property of the binary search tree. So we cannot violate it. So for example, if let's say we want to insert the number 15, so we cannot put 15 here, because then 15 is not smaller than 29, right? So in that case, 15 is actually not larger than 29. So it cannot be on the right. So if I put 15 here, it's going to violate the binary search tree. So I need to preserve it. So how do I preserve it? So I need to find the right place where once I put 15 in, then every single node is still going to satisfy the property that anything on the left is smaller, anything on the right is larger. Now, one way we can do it is to first search for the number that you want to insert. Now, you don't expect to find it there. So, but you can search anyway. So 15, you start at the top. 15 is smaller than 29, so you go to the right, to go to the left. 15 is larger than 14, so we go to the right. 15 is smaller than 24, so we go to the left. But there is nothing to the left of 24. And because there is nothing to the left of 24, we can put 15 there. Because once we put 15 there, next time when we search for 15, we expect to find it there anyway. Now, essentially then insertion is preceded by a search, which then fails at some point, and then it's going to insert the new node right at the point when it fails. So this is the searching method. And let's look at this inserting method. So the inserting method essentially has a similar structure as the searching. So it begins with checking whether value is there. Otherwise, it's going to decide whether to go to the left or to the right. Now, but if the search doesn't fail yet, it will continue, just like the searching will continue. But right at the point when the root left is none, meaning the search has failed, we are going to insert it right at the point where it fails. Essentially, it is searching followed by insertion at the point where the search fails. So that's the concept of the inserting into new node into the BST. Now, in this way, it is also important to know that we don't actually sort the tree. So we don't give you a tree and then we ask you to sort it. And can I do insertion sort or merge sort and so on? That is not the point of this. When you deal with the binary search tree, you construct the tree from scratch. So for example, how did this tree come into being? So this tree initially was empty, and then we put 29 in. When we put 29 in, it becomes a root. So the next number that comes is either 14 or 50, right? So because then 14, if let's say 14 goes in, 14 is smaller than 29, then you can insert it on the left. So the insertion process, iteratively, is going to construct a binary search tree that would have this structure of being sorted in some sense. So here, by constructing the tree, one at a time, you're going to get a binary search tree. Now, you can keep inserting, but at some point, you may need to remove the nodes, right? So then there is a concept of how do I actually remove things from the tree. Now, the problem with removing things from the tree is that we may then cause a problem in terms of whether we can still preserve the tree structure or whether it's going to get splintered or whether we are removing nodes unnecessarily. So we're going to look at three different scenarios from the simplest to the most complex. The simplest one is that we are going to remove a node that is a leaf node. That means it has no child. So an example of that is 27. So in this case, 27 has no child. So if you say, okay, let's remove 27, so how do you remove it? So first you find it, right? And then once you find 27, then you kill it, right? So you remove it from the tree, and then it's gone. But how do you actually remove it from the tree? Because the existence of 27 is not actually maintained by 27 itself. The existence of 27 is actually being recorded by its parent, 24, right? So to remove 27, what you need to do is to tell its parent, 24, okay, you have a right child, or you used to. Now it's not there anymore, right? Just remove it from disown the child, and then this becomes none. So essentially 27 is going to be dangling, and then you essentially remove 27 from the tree. Now, the next case is when you want to remove a node that only has one child. And an example of that is 24. So 24 has one child, which is 27. Now, you can do the similar thing. You can find 24, and once you find it, you can say, let's remove it. Let's tell its parent that 24 is not to be there anymore. So you go to 14, and you say 14, okay, 24 is no longer your child. Now here there is another problem, because essentially you are penalizing 27, right? 27 doesn't do anything wrong. The parent does something that you want to remove it, but you want to keep 27 around. So then the way to do that is that we're going to bypass it. So if 24 only has one child, which is 27, then you just go back to 14 and tell 14, now your child is no longer 24, you have a new child now, it's 27. So you just bypass it. So in that case, everything will still be at peace. Now, the complex case comes when you're trying to remove a node that has two children. So he has two children now, and the problem is that then which child is going to inherit its place, right? So that's a problem. All right, so let's say if you think about 29, for example. 29 has two children, 14 and 50. So if we follow the same idea, then we have to say, all right, so let's find something that can replace 29. Now, for example, you can take 14 and you can say, since 14 is a child, can we replace 29 with 14, one of his children? But if you replace 29 with 14, so then 14 becomes the root, right? Let's say, then where is 50 going to go? Because 14 already has two children. So then there isn't a good way to do that. Now, the easiest, the most convenient way of removing a node that has two children is to find a replacement that is as close as possible to the node that you're trying to remove. So for example, you want to remove 29, it is best that you replace 29 with something that is as close as possible to 29. And what is as close as possible to 29? So in general, it will be the largest number on the left or the smallest number on the right. And you can always find it. If you want to find the largest number on the left, you just go to the left and then keep going right. At some point, you find the largest number. If you want to find the smallest number on the right, then you go to the right and then you keep going left. But in this case, there is nothing more, so 50 is the smallest number. Now, if you replace it with the largest number on the left or the smallest number on the right, you're going to cause the minimum operations. Because in this case, it doesn't cause a lot of problems. So for example, if you're going to replace 29 with 27, you just take out 27, plug it there, right? And then everything's fine. There is no other problem. Now in some cases, you might end up with a case like this where you want to replace 29 with the smallest number on the right, which is 50. But to replace 29 with 50, you first need to remove 50. So it causes a chain reaction. So in that case, before you can replace 29 with 50, first you remove 50. And how do you remove 50? You first replace it with 71, right? Because 50 only has one child. So it's recursive. So then 50 gets replaced by 71, and then 50 is going to replace 29. Then you still have a binary search tree. Now, which one do you go? Do you go on the left or do you go on the right? Do you take the smallest number on the left, or do you take the smallest number on the right, or the largest number on the left? So you can do either one. Generally speaking, it's going to be correct. But one of the properties that we try to go after when we deal with binary search tree is that as much as possible, we want the tree to be relatively balanced. So that means that you want the left side and the right side to more or less have a relatively equal number of nodes. Because in that case, then when we talk about binary search tree, in terms of trying to cut down the search space into two, left half and right half, it's more effective if the numbers are almost equal, right? So when you go to the left, you're going to cut half. But if all your nodes are on the right side, or all your nodes are on the left side, by going to the left or to the right, you're not actually reducing any search space, because the tree itself is not balanced. Okay? Now, what so far we have learned, essentially just the structure of the binary tree and the structure of the binary search tree. Now, these are different types of data structure that will maintain the relationship among objects in a certain hierarchical sense. Now, you may then decide to keep your data in one of these forms, so you need to be able to iterate over them, and that is why you have something like the traversal orders. This is the way to systematically go through every single one of them. Now, in alternative cases, you might wish to sort the tree. You might wish to arrange them in a particular order that allows you to find elements in an efficient way. And you can fashion them into a binary search tree. Now, last week we talked about priority queue. So priority queue can be implemented in terms of a binary search tree. Now, if you think about this, every time a new node goes into the queue, so we just put it into the binary search tree. So for example, if this is the current priority queue, and you want to remove the node with the highest priority, let's say, is 2, right? So you just need to remove the one that is the smallest one. So do you always know how to find the smallest one? Just go to the root, keep going left. At some point, you're going to find the smallest one. If you want to insert a new one, the new one is just going to be inserted into the queue as if it is being inserted into the binary search tree, right? So you have a new element that joins the queue, then you just insert it into the binary search tree. It's going to go down and find its rightful place, and you're just going to stay there until it gets dequeued. So that's why, essentially, binary search tree can also be an implementation for the priority queue. Right? Any questions?